Hello, I'm Daniel van Eeden. Today I will be narrating this presentation. This is because the audio track was not recorded correctly initially. So today we will start with some introduction, then we will go over some protocol features. So I'm Daniel van Eeden. I'm working for PingCAP on TiDB. This is a MySQL compatible database and it's written in Go. I'm also a long-time MySQL user, and I'm also interested in the MySQL protocol because of various contributions to projects like Wireshark, which is a MySQL protocol dissector. Also, Go MySQL, which is a framework for working with the MySQL protocol in Go, both a client driver and a server implementation is provided by this project. And then, of course, TiDB and MySQL. The last on the list is DBD MySQL. This is the database driver for MySQL in Perl. So the first protocol feature we're talking about today is session tracking. Session tracking adds extra information into the OK package that the server sends back to the client. The available information consists of the default schema, for example, after using like a use and then the name of the schema. But also think about like what happens if you drop a schema that you're currently connected to. And then there are session-specific variables, user-defined variables, temporary tables, and prepared statements. For some of these, like user-defined variables and prepared statements, the information is limited to that something in the session changed and not exactly to what in the session changed. and then some information about how to enable these extra information that's put in the OK packet. The first setting is session track state change, and you can set it to on or off. And if you set it to on, which I think is the default, it will give you some information about like if a user-defined variable has changed or not, and a few other things. The second one is session track system variables. By default, this is a short list of system variables that are being reported. If you set it to star, then it will give you all the system variables. However, the system variables for which this matters is mostly the ones that have to do with a character set and collation. So for example, if you do a set names Latin 1, then of course there are a few variables that change to have the collation and the character set. These will be reported. Session track schema, this will report changes in the default schema. You can set it to on or off. And then there's session track GTIDs, which you can set to all GTIDs. Then you get a full set of the GTIDs. And with own GTID, you only get the one of your transaction. And I think the one, the default is the own transaction one. And that's usually the most important one and the most useful one. And then there's a session track transaction info, and you can set it to various settings, but the most useful one is the characteristics setting, and then it will give you information if your transaction is read-only or read-write and a few other things. So now we get to use cases. One of the use cases is to get the statement ID, which you then can use for later lookup in the performance schema tables. So you run your statement, you get the ID, and then with that ID, you get some information from performance schema for that specific statement. Note that in the MySQL shell, this will by default report the statement ID if it's sent. It will also show you the GTID if that's configured. The MySQL client does not do this. The next use case is getting the GTID, which you then can use for consistent reads from a replica. And we'll have an example in the next slide. And then there's the set names Latin 1, which will result in changes to the character set client, character set connection, character set results. And also the other use case is to get some transaction information that's useful for proxies. For example, if you want to do session migration. So the next slide is about example for consistent replica reads. So your application is doing an insert. Here, step 1. And that goes to a MySQL primary, which then reports back the GTID of that transaction with session tracking. And then your program can go to a secondary and actually execute a select wait for executed GTID set with the GTID it got from the primary. Then it will get back a result or a timeout. Besides the GTID set that you specify, you also specify the timeout that you want to use. So in this example, we will be using a delayed replication of 10 seconds. So there will always be a replication delay of 10 seconds between the MySQL primary and the MySQL secondary. The select wait for executed GTID set can be used as a separate statement, or it can be used as part of another like usual select statement. So here we have the output of the test program. Note again, this is with a source delay of 10 for a 10-second delay between the primary and the secondary. So we're creating a test.t1. So we create a new table. Then we're inserting a record into test.t1. This is all being done on the primary. Then we get back the GTID. And then we are using the select sum val from T1 to get the value from that column, set of columns. And the reported value is 882. So this is also what we expect to get if we are using the same statement on the replica. So we're doing the same statement on the replica. It's returning 840 instead of 882. This is because of the replication delay. The replica hasn't yet seen the inserts on this table. So what we're now going to do is to run the select wait for executed GTID set with the GTID that we got from the primary, and then a timeout of 3 seconds. So after a few tries, we actually get a success back. And after we get the success back, we know that we can run a select sum val from T1 and actually get back the right value. Because we now know that it has seen all the inserts that we did on the primary, that everything has replicated. The next feature we are talking about is compression in the MySQL protocol. Compression trades CPU time against bandwidth. This could be useful for slow links, like doing DBA work over a slow hotel Wi-Fi, or in cases where the bandwidth might be expensive. So a lot of cloud providers bill you for like the network bandwidth that you're using, especially between different regions and between the cloud and the wider internet. So this could be a useful tool. Compression was introduced in the MySQL protocol a long time ago, almost from the beginning. It was never very popular because of the overhead that it was bringing and the very few benefits that it was providing. So compression is disabled in the MySQL protocol by default. Note that this is only true for the classic MySQL protocol. In the MySQL X protocol, this is actually enabled by default, but today we're not talking about the X protocol. So the compression that used to be in MySQL was all based on zlib, also known as the deflate compression algorithm. So recently support for zstd, that was created by Meta, was added. So zstd does a way better job in compressing things, but because it was recently added, not all the client libraries and applications have an option to actually configure this. So in some cases you might need to upgrade your client library to be able to use this. With the MySQL client, you can use this by using MySQL with the -- compression algorithms and then a list of algorithms. It's usually best to only specify a specific algorithm like zstd, because that's usually the better option, because if you give both options, it's not using zstd, it will be using zlib, which is not the best option. Note also that with zstd, there's the option to specify the compression level. That wasn't the case with zlib, because the protocol didn't allow for it. But with zstd, this is possible. By default, the level is 3, and I think it goes to like 20 or so. Compression can also be used for replication by using the source compression algorithms option and the source zstd compression level option in the statements for replication. But for replication, you might want to use the binary log transaction compression instead, because that also compresses the files, the binlog files on disk, and it's also doing resulting in less network traffic. You can use both together if you want, and that's also possible. So in the client it looks like this. It says protocol, compressed, algorithm, zstd, and zstd level is 3. So a MySQL compressed packet can contain multiple MySQL packets, and a single MySQL packet can be split into multiple compressed packets. So there are like 2 layers in the protocol. The maximum size of a compressed packet is just under 16 megabytes, and regular MySQL packets are also limited to just under 16 megabytes. If you're sending large values like 500 megabyte 1 column update, then this will be sent in multiple packets. And the max allowed packet does not set the maximum allowed packet size. It sets the limits for the message that's being used, so that can be a bit confusing. A compressed packet has a payload that can be compressed or uncompressed. The sender can decide if it wants to compress the packet or not. If the compressed version of the payload is larger than the uncompressed version, the sender is usually not sending the compressed version, but it's just sending the uncompressed version. And also, if the payload is less than 50 bytes, then it's usually sent uncompressed and it's not even attempting to compress this. And the compression is done in MySQL on packets of up to 16 megabytes. And this is severely limiting how useful and efficient the compression is. The drawback is that there's an overhead of 7 bytes per packet, whether or not it's compressed or not. But if you enable compression, then this is the overhead. And then there's the overhead of CPU usage. This can be especially important on the MySQL primary that's already heavily loaded. So what happens if you run a select repeat fosdem 5000? This is a query of 46 bytes, which is less than 50. So the query being sent to the server will not be compressed. It will be using the compressed protocol, but the payload is not compressed. So the compressed header is 7 bytes, regular header is put in there, then the command, the com query, and the parameter information might be there depending on if there's anything configured or not. And then there's the actual statement. So with compression enabled, this is 46 byte, and without compression, you save on the header, and then it will be 39 bytes. So it adds 18%, which might seem much, but actually not that much. So compressing zlib with zlib, the compressed packets that are set for the return result set will be 3 packets. The first packet being 124 bytes compressed and 16K uncompressed with the column count in there, the field packet describing the first column, and the row packet, the first part of the row packet, and the second compressed packet has the second part of the row packet and is 33K or 34K. And then the last packet is just 11 bytes and it's not compressed. And it's just the OK packet. So the row packet is just over 50K. Note that there are 3 packets because the net buffer length is by default set to 16K. This limits the size of the first packet, and because that's what the buffer is allocated for this first packet. So we can increase the net buffer length to say 100K, and then the whole thing, the whole result set is sent into a single compressed packet of 197 bytes compressed and just over 50K uncompressed with everything in there. So because it's a single packet, there's a little bit less overhead when it comes to bytes. And then we can also do the same thing, but with the Z standard. Then we get a single compressed packet, and it's compressing to 96 bytes. So that's about half of what the previous zlib test. And then we can change the compression level as well. And that doesn't really save much. If we set it to 22, we get down to 94 bytes. So here's the overview of the compression. Like we can put it into like one packet with only 94 bytes if we really try hard. Seeing how this works really needs a tool like Wireshark, because MySQL isn't great in actually giving you monitoring information about compressed packets. So the monitoring information that you get is you get the bytes sent and the bytes received in MySQL. You can compare these to your OS counters and compare this to like previous values. And then you can see that if it's sending a lot of data and actually compressing it, you will see the bytes sent and received go up a lot faster than the actual network packets from the OS counters. Because the bytes received and the bytes sent, that's the uncompressed version. For the X protocol, there are a lot more things you can monitor. So this is what compression monitoring looks like. You see the bytes received, bytes sent. Then you're sending some statements. Then you check the bytes received and bytes sent again. Then you can see that we only sent 262 bytes, while the result set was much bigger than that. Other things that might be useful here is system tab. This is sort of dtrace for Linux. And then you get some more information. But also if you run MySQL in debug mode, you get some more information in the trace files that you can create with MySQL. So possible future work for this is to add zstd to more drivers and connectors and tools. Maybe look into BPF for instrumentation, for compression, and maybe also improved metrics in the server and or client. And it would also be great to have more open source OTel trace span integration. And it looks like Oracle is going to make this open source. Previously, this was only available in MySQL Enterprise. Then the next feature that I want to talk about is connection attributes. Connection attributes are key value pairs that are set per connection and is very useful for troubleshooting. These key value pairs that are just metadata and they are visible in performance schema. Here's an example. Here you can see that the program name is MySQL. This is being run with by my user account. And the version is 950. This was on a Linux machine, on an Intel CPU. And you also get the process ID. So that's great if you want to figure out like what clients are being used with your database. And maybe you want to make sure that all the clients are capable of maybe new TLS settings that you might want to introduce. Or you might want to know like where this weird connection is coming from. Because it wasn't on your list of things that you were expecting. So these things are being set by connectors and by drivers. Usually then the name starts with an underscore. Or they're set by applications like the MySQL client in this case. That's setting the OS user and program name. Note that you can also add your own, and these things can be very useful. So the things you might want to set in your application are, for example, the application that's connecting, maybe like report generator, Slack bot, payment gateway, because that gives the DBA much more information about what the connection is about. You can also give the application version. That can be a great help if you're like upgrading applications or doing a rolling restart and want to know if everything is on the new version. The production environment, maybe it's production, acceptance, test, these kind of things. And the job name, like a specific ETL job. Note that this only works if the connection is only used for like a single job. Maybe information about the connection pool, the name of the connection pool, some ID, etc. Or maybe the management information, but like this, the connection is for something managed by team Chaos Creation Team 6. And the thing you should not do is things that change over the lifetime of the connection, because connection attributes are statically assigned for a connection and cannot be changed during the connection. So the next feature is query attributes. So the connection attributes are connection-based, the query attributes are query-based. So each of the attributes has a type, a flag, a name, and a value. Connection attributes have only a name and a value, but here we also have a flag and a type. This makes it very similar to prepared statements. So extra functionality is available in the server with a component named component query attributes. This is not required to actually use query attributes, but just some extra functionality. So here on the left you can see a Python application connecting to MySQL and setting two attributes, the proxy user and a user ID. Note that these are per query, so they can change during the connection. So with these attributes, you see them on the network, and you can see them in the server. Because they are per query, to see the values that you're getting, it might need a little bit more work and not as easy as with connection attributes. But the MySQL connection attribute string function that's provided by the component, that can actually show these. And this works for all the different types, because the string part of the function name means the output type, not the type it's working with. So with the Python program on the left, you can send the proxy user and the user ID. It gets a value, a type, and a flag. And the flag is basically setting if it's a signed or unsigned value for integers. So query attributes can be used to send metadata about the query to the server. Examples are like a web page, end user, or application file and line number, maybe a tenant ID, experiment ID. So it's basically the same as just putting some metadata into the query itself in a comment. But it has a few benefits. First off, it can be parsed reliably, both on the network and on the server side. And it has type information, and it doesn't result in hard to read queries, because here you can also already see that the query gets quite long to read. And if you're looking at like a report and you only see like the comments instead of the actual queries, this might not be what you want. So with query attributes, we can send a query and a set of key, type, flag values. It's quite similar to prepared statements, but prepared statements don't have a name and don't have a key or key. And prepared statements take multiple round trips. Many connectors and drivers implement prepared statements on the client side to avoid the multiple round trips. Query attributes could form the base for a single round trip prepared statement, where you're sending both the query and the parameters of the query all in the same network packet. Note that Postgres does support something like this, where you're basically sending the statement, and then in the next network packet you send all the parameters for that statement, but these can be combined and sent to the server at once. With MySQL, you first need to send the statement, get back the ID of the query, and then in the next packet you send the ID of the prepared statement and the parameters, which isn't as efficient. So query attributes could maybe in the future be used to improve this. And this was already suggested in 2021 by Joro on FOSDEM. And note that X protocol can also do prepared statements with a single round trip. I'm skipping to the pre-authentication version info in Go. So the MySQL version is being reported by the server as soon as you connect. So if you just read the bytes that the server is sending to you after connection, and then you can easily parse out the version. For the version to read, you first need to read the header, which is 4 bytes. You get the length of the actual packet, and then you read the whole packet, and then you start reading the place where there's the version information. So you can actually quite easily do the same in Ada. And the whole thing that I want to say here is that getting version info from MySQL is easy. You do not need authentication. You don't need a full session. So if you want to just do like some network scanning and figure out like what MySQL servers are on your network, you can just connect to everything that looks like it might be MySQL, because maybe it's listening on port 3306 or something similar. Then you can just connect and see what network version what version they report. And note that if you're connecting to something like a proxy, the proxy might give you a temporary version and not the actual version of the server that you eventually connect to. So here you just quickly saw the MySQL version tool, where you can see that the version is being reported. And this is usually way quicker than actually getting a full authenticated session and then running a select version. Note that some client drivers can also use this to get a version more easily without extra round trips. And scanning for this can be very good if you want to scan for MySQL versions on your network, especially if there are maybe forgotten or unauthorized servers on your network. This doesn't need authentication, so that makes things a lot easier. Also note that because it doesn't need authentication, it also means that anyone can do this, also people with less good intentions. Note also that because select version and the version in the handshake doesn't have to be the same, and that you might want to make sure that you get the right version for the right job. Quick statement about X protocol. When creating this slide, I've been working on X protocol support in Wireshark, which I implemented. So X protocol is based on protobuf and a few extra things around that. So in Wireshark, you can now use dump traffic for X protocol and actually decode the traffic, which is quite nice. X protocol is not used a lot. Most things are all using the MySQL Classic protocol, and I think some other databases like MariaDB don't even implement or work with the X protocol. The main feature of the X protocol is pipelining, but also being able to do compression in a slightly better way, and the ability to do like create, update, and delete things that are more similar to what you would expect from like a document database. Then there's cloning, which we'll skip over. Skipping to MariaDB enhancements. So in MariaDB they have client progress. So if you're in an alter table that takes a long time, it will give you updates about in which stage it is and the percentage of that stage that it has done. This is quite similar to the notice frames in the MySQL X protocol, but this is done in the regular protocol as a special kind of error message that's being sent while the alter table statement is running. This has also been implemented in Wireshark, by the way. And then there's the timeout reason. So it can be difficult to see if your network connection just dropped, maybe the server died, or that you were hitting a timeout. This was improved. So now the server tries to send you a message after it hits a timeout. In some cases you actually get to see this message, or you might see it on the network trace. And this can help you to actually identify that it was a timeout that you were hitting, instead of like an issue with a TCP connection disappearing. So these were all the slides I had for today. The slides are also available online. Feel free to send me an email if you have any questions about this. Thank you for your attention.